Hello. So we're going to start 6.3, finding solutions of differential equations about regular singular points, right? So last time we had our second order differential equation, right? Homogeneous second order differential equation, and we wrote it in the normal form. So that's the y double prime plus p of x y prime plus q of x y equals 0. And we said that as long as the p and the q, right, these coefficients here, right, these could be, polynomials or any functions, if they're analytic, right, that means they have a power series. Right? So analytic means that you can write p and q as a power series. At a particular point, right, expanded about x0, then we said that x0 is an ordinary point, right? And if it's an ordinary point, then you can always write the solution as some power series expanded at x0, right, which is usually 0, right? This is usually cn x to the n. But it doesn't have to be, right? It could be about any point. But 0 is the one we like to use the most. It's the easiest. Right. And then we said that if p and q are not analytic, right, so if they're not analytic, that means p and q do not have a power series at x0, then x0 is a singular point, right? And last time we said that singular points are bad because there's no guarantee we can write these as power series, right? That you can always do for ordinary points. You can not always do for singular points, right? So yeah, so now we're going to concentrate on what happens when you do have a singular point. And it turns out that not all singular points are the same. So it depends on the form of this p and q. Okay, so right, if I take x minus x0 and multiply that times p of x, right? So if that is analytic, right, and let's give this a name. Let's call this lowercase p of x, right? So if this is analytic, well, actually, before let's do both conditions here, right? So x minus x0 times q of x, let's call that lowercase q of x, right? I'm sorry, x minus x0 squared. Okay, so if both of these functions, right, if both of these functions are analytic, that means they have a power series. We can expand little p and little q as a power series at x0. Then we say that x0 is it's still a singular point because the capital P and capital Q might not be analytic. But if this lowercase p and q, that is if you multiply p by a linear factor of x and q by a quadratic factor of x, that those functions are now analytic, then x0 is called a regular singular point. Okay, so yeah, in some sense, a regular singular point isn't that bad, right? We can deal with that. In fact, we will be able to write the solution, right, y as some sort of a series. Okay, not necessarily a power series, but an infinite series in general. Okay, so yes. Now, what happens if these are not analytic, right? What happens if you have to multiply, say, by x minus x0 to the third or to some higher power, right, for it to be analytic? Then we say it's an irregular singular point. So otherwise, right, x0 is I'd like to say non-regular, right? It's an irregular singular point, or sometimes called an essential singularity, but we'll stick with irregular singular point. And those are the really bad ones, right? Those are the ones that we might not be able to do anything with. If we're lucky, we can, right? It's not, right? It just means that there's no guarantee that we can write the solution as any kind of a series, right? For regular singular points, you can write it as a series. For irregular points, possibly, but not guaranteed, right? And not ones that we're going to deal with, right? So we're going to deal in this section, right, exclusively with just regular singular points. Okay. And there might be some mention in the homework about some irregular singular points, but we're not going to deal with those, I don't think. Okay. So first, just some examples of how we get these regular singular points. So let's look at the following example. Okay, we have x squared y double prime minus 3xy prime plus 4y equals 0, right? So right, in this form here, it's going to be very hard to tell because, right, the p of x, the capital P of x, is not the negative 3x, right? We have to divide by x squared first. So we want to first put it in, right, our normal form. That's normal form here. And in this form, we can see that our lowercase p of x, right? So yeah, you can see that x equals 0, right, is not an ordinary point, right? So both p and q, capital P and capital Q, are not analytic at x equals 0, right? So this is a singular point. X equals 0 is a singular point, right? So let's calculate this little p of x here, this lowercase p of x. It's just going to be x times capital P of x, which means it's negative 3 over x times x, which means it's just negative 3. And negative 3 is a constant, so it's certainly analytic. Analytic, right? It has it has a power series that's trivial, right? It's just the C0, so C1, C2, C3 are all 0. But it is it's technically a power series. It's just a terminating one. So this is definitely analytic, right? And our lowercase q of x is x squared times capital Q, which is, 4 over x squared times x squared. That's just 4. And that's also a constant. So obviously when you get a constant, they're going to be analytic, right? There's, you're not dividing by 0, right? So x0 is a singular point, but because both lowercase p and lowercase q are analytic at x0, it is a regular singular point. Okay, right? So that's good. And maybe you remember that, right? This is actually you know how to solve this, right? This is a Cauchy-Euler equation. Euler-Cauchy, Cauchy-Euler, right? Because notice the order of the derivative. It's second order derivative and then quadratic x squared, right? This is first order derivative and then x to the 1, and this is 0 order derivative, right, times x to the 0. So it fits the Cauchy-Euler, so you could solve it that way. And so there's no reason to try to even solve it using a power series. I mean, you can, but it's going to be a terminating one. And it might not even be a power series, right? All right, so let's look at another one. Okay, example 2. So we have y double prime minus 5x over x minus 2 squared times y prime plus 6e to the x over x minus 2y equals 0. Okay, so first note that this is already in normal form, right? Because the leading coefficient is 1. So this is already in normal form, right? And that means we can identify our capital P as, well, all of this, right? So negative 5x over x minus 2 squared. So I'll just write that over here, negative 5x over x minus 2 squared. And our q of x, capital Q of x, is just 6 e to the x over x minus 2. Okay, so what do we notice? We notice that in the denominator we have a factor of x minus 2, so that tells me that x equals 2, right, is a singular point. Right? So these functions here, p and q, capital P, capital Q, are not analytic at x equals 2. You cannot write them as a power series, right? Well, what happens, right? You get a negative exponent, right? You get x minus 2 to the x minus 2 to the negative 2. Right? Remember, for a power series, you're starting at 0, right? So way up here, right? For a power series, you're starting at n equals 0. So all the exponents of x, or x minus x0, right, cannot be negative. Okay. So we know it's a singular point. Is it a regular singular point, right? So x equals 2 is a singular point. Is it regular or irregular? Well, so we have to multiply, right? So we're going to try to do lowercase p here. Lowercase p of x is going to be, in this case, x minus 2 rather, times capital P of x. And, right, remember, for the p, you're only multiplying by x minus x0 to the 1. So you see what happens, right? You get negative 5x still over x minus 2. And this is not analytic at x equals 2, right? You're still dividing by 0 here, right? And so you're still going to get a negative exponent. So this is not a power. You cannot expand this as a power series. Well, you can expand it as I guess as a geometric series, but again, it's not analytic at x equals 2. You can expand it about some other x, but not at 2. And that's what we're looking at, x equals 2 here, right? Right, so for that reason, this is a singular point, but it's an irregular singular point. Right. Irregular singular point. Now, we didn't check the lowercase q. The lowercase q is satisfied by this, right? Because you're multiplying x minus 2 squared times q of x, capital Q of x, and you actually end up with 6 e to the x times x minus 2, which is analytic at x equals 2. In fact, it's analytic everywhere, right? Oops, sorry. But remember, both of these have to be true, right? Both of these have to be true. Both the lowercase p and the lowercase q have to be analytic for your x0, in this case R2, x equals 2, to be considered a regular singular point. Since only one of them is true, it's an irregular singular point. Okay, so I hope that helps distinguish between regular singular points, which are good. In fact, we're going to deal with those, and irregular singular points, which are bad, because there's no guarantee we can solve these differential equations here at irregular singular points. Right. In some cases you can, right? In some cases you just get lucky and it works out anyways. But in a lot of cases, in fact I'd say most cases, irregular singular points, you're not going to be able to solve those, not in any systematic way. Okay. So I guess let's do our next example, and in fact we're actually going to try to solve a differential equation. We won't bother solving these, certainly not example 2. We could solve example 1 using a series, except it's Cauchy-Euler, and that's probably the much easier way to solve it. In other words, assume, for example 1, that your y is just going to be, x to some power m, and, work it out what that power has to be. Much easier, right? Because you're only dealing with one basically one term of the power series rather than deal with a whole series of terms. Okay. Okay, so let's actually try to solve this equation here, xy double prime plus 2y prime plus xy equals 0, right? So definitely not Cauchy-Euler, and definitely nothing we've dealt with so far. And so remember, first put it in normal form. In normal form, this is y double prime plus 2 over xy prime plus y equals 0. So we just divided both sides by x. And so you can see that in this form, your capital P, right, is 2 over x, which is, 2 over x, which is not analytic at x equals 0, right? So x equals 0, right, is our singular point, right? And by the way, q of x is just 1, so that's analytic, no problem there, but our capital P is not, right? Our lowercase p, right, we have to multiply capital P times x, and so that's just, well, that's just 2, right? 2 over x times x is 2, and that's analytic, right? And our lowercase q would be x squared, which is definitely analytic, right? So, right, so constants and x squared, these are both power series, and in fact, they're trivial power series, they're just one term, right? So x equals 0 is not just a singular point, it's the good kind of singular point. It's a regular singular point. Okay? So what do we do when we have a regular singular point, right? Well, without knowing what to do, let's just see what happens if we attempt the same thing we did for ordinary points. Remember, if x equals 0 was an ordinary point, we would assume that y of x is just a power series, right? Going from 0 to infinity, and we have Cn x to the n, right? Yeah, because we're expanding this at x equals 0, right? That's the easiest way to do this. So, right, so we're centering this series at x equals 0, and we're going to assume that it's a power series. And we're going to do the same thing that we did last time, and we'll see what happens, right? We'll see what happens. Again, in general, this may not work, right? When you have a singular point, right, there's no guarantee that you're going to get a power series out of it. Okay, so let's go through this, right? In step 1, we just assume that this is a power series, right? And we need the derivatives, right? So we need y prime, which is our, remember we start at 1 now. Later on we'll see that's not going to be an issue. You can also start at 0, but right. So this is n times Cn, n times Cn, x to the n minus 1, and then y double prime is going to be, n starts at 2 now, n times n minus 1, Cn, x to the n minus 2. Okay, so now we just plug these into, well, instead of doing the normal form, we're going to plug this into the original equation here, right? Yeah, because it's easier to multiply by x than to have to divide by x here, right? So let's actually calculate this now. Let's calculate x y double prime plus 2y prime plus xy, right? Because we're just going to, in the end, set that equal to 0. So before we do that, let's see what we get here, right? So we're going to get x times the second derivative. Oop, not at 0, we're starting at 2. Right? So we have n minus 1, Cn, x to the n minus 2, plus 2 times y prime. And for y prime, that's up here, Cn, x to the n minus 1, and then plus x times y. Y, of course, starts at 0, and it's just your Cn x to the n, and this is all equal to 0, right? So, yeah, now it gets tricky, right? Because we want to write this all as a single series, as a single power series, right? In terms of the same powers of x, right? Oh, actually, before we do that, notice that this x can come inside here, right? And so this will actually be just x to the n minus 1. Yeah, can I just fix that? Because I don't feel like rewriting it all over just for that. Okay, so I brought that in. And we could have brought in the 2 as well. Right, but we'll do that on the next step, right? So now let's think about what the lowest power of x that's common to all three of these, right? So for the first term here, we get x to the power 2 minus 1, which is x to the 1. For this one here, when n is 1, this is x to the 1 minus 1. This is x to the 0. And this will also be x to the 0. So the highest power for all three of these, or I'm sorry, the lowest power for all three of these is x to the 1. Okay, so what that means is we're going to have to bring out the x to the 0 term here. So let's do that, right? Let's ignore this one for now. And so the x to the 0 term is going to be, well, 2 times 1. Remember, n is 1, right? N is 1. The exponent is 0. So this will be 2 times 1, that's the n, times c1 times x to the 0, plus, and then, oh, you know what? I didn't bring in the x here. Oh, yeah. Okay. So this should really be x to the n plus 1. And so, yep, I take that back. This is not x to the 0. This is actually x to the 1 when n is 0. Right? So this is x to the 1. So I think then this is the only term on the outside. Yeah, I think, okay, so hang on, it's never mind, right? So this, I think, is the only term, the x to the 0 term, right? Yeah, so again, I'm bound to mess up sooner or later here. This is going to get, well, you'll see, it's very easy to get lost in the details here. But yeah, so it turns out this second term here was not necessary because it starts at 1. Right. So x to the 1 is the first term there. Okay. Well, okay, so now we're starting at 1. And I think all three of them will have an x to the first power in it. And so this one here, well, do we want to re-index now? I'll do that on the next step. I know, I really want to take this slow here. Right? So I'm just going to rewrite all this again. There's a 2. So I'll bring the 2 inside. Right. Oh yeah, and this x isn't here anymore because I made it x to the n plus 1, right? So n equals 0. Cn x to the n plus 1. Right. And that's 0. Okay. Now we need to reindex because you can see that these power x to the n minus 1, this is x to the n minus 1, this is x to the n plus 1. We got to be consistent here for all of these here, right? So yeah, let's just do them individually. So I guess we want this to be, if we're starting at 1, we want this to be n, right? So let's call it k, right? So here, k is going to be n minus 1. And if we do that, then n is just k plus 1. So we can rewrite this series here, oops, in terms of k. So k now starts at 1 and goes to infinity, right? Because if n is 2, k is 1. And then this will be, instead of n, it'll be k minus 1. And instead of n minus 1, it'll be k minus 2, right? So it's, wait, did I get that backwards? So n is k plus, I did get it backwards. N is k plus 1. And n minus 1 is k plus 1 minus 1. So it's just k. hang on. So yeah, this is a plus 1, this is just k, right? And this will be c subscript k plus 1, and this will be x to the k. All right. I think I got it right. If not, let me know. All right, let's go on to the next one here. So we want this to be our k. So same thing here. I'll just move this over here, right? So, yep. So notice that this is n equals 1. We already have the 0 term. That's the one out here. So we can still start at k equals 1, right? So 2 times n, but n is k plus 1. So this will be c sub k plus 1 times x to the k, right? Okay. And then finally, well, if we want this to be k, here for the last term, this is going to be a little different. This is going to be n is equal to, or rather k is equal to n plus 1, which means n is k minus 1. Okay. So, yeah, so we're starting at k is equal to 1. Right, so this will be c subscript n, which is k minus 1, times x to the k. Right? Yeah, again, we're starting at k equals 1 because this was n equals 0. Right? Okay, so, and that still equals 0. And don't forget the 2c1 in front here. Okay, so now, I think we can combine these all as a single series, except the first term, the 2c1, right? And now we have k going from 1 to infinity, and let's just group all this together. We have k times k plus 1 times ck plus 1. Oh, actually, can I combine that with this? Right? So, oops. Yeah, so before I write the ck plus 1, let's add the 2 times k plus 1, right? All of that times ck plus 1, and then plus the ck minus 1, right? And all of that is times x to the k, and that's going to equal 0. Okay, so I think I got that. Let me just check for a second. Yep, okay, that looks right. Right. So our next step is to set this equal to 0, right? Remember, when you have a power series that's identically equal to 0, I'll just call it an next to the n equals 0, right? So if this is 0 for all x, or at least all x on some interval, then the an's all have to be 0, right? So what do we have on the left here? Well, we have 2c1, so that has to be 0, which means if you divide by 2, c1 is 0. And then this whole coefficient here, that's my an, right? That's my coefficient of x to the n, or in this case, x to the k. All of this has to be 0. Okay, I'll leave it like this for now. ck plus 1, and then plus ck minus 1 equals 0, right? Okay. So this is going to give us our recurrence relation, right? The idea is we're going to solve for, let's say, the ck plus 1 in terms of the ck minus 1, right? So the idea is I'm just going to subtract the ck minus 1 from both sides. And on the left, that's going to give me, so notice what I can do here. If I factor out the k plus 1, I just get k plus 2 times k plus 1 times ck plus 1, and that's going to be negative ck minus 1, right? Right. And then I can divide both sides by k plus 2, k plus 1. And so these cancel, and we solve for ck plus 1. So let's see if I can squeeze that in here. So ck plus 1 is going to equal negative ck minus 1 divided by k plus 2 times k plus 1. I hope that's big enough, because this is actually the important thing here. This is our recurrence relation, right? So, yeah, in fact, let me write it over here. I'm just going to write it bigger. Give me 1 second. Okay, there we go. There's our recurrence relation, right? And so what do we do with that? Well, we just start plugging in k's and seeing what all the c's are, right? What's C0, what's C1, what's C2, what's C3, and so on, right? So, yep, let's do that. Let's do that here. So let's start with C0. Well, this doesn't tell us anything about C0, right? So C0 will be our arbitrary constant here. Okay, right? And so let's say, so here, k would have to be 1 for this to be C0. I'm going to do that over here. So k is 1, right? That means we're going to get C0, and this will end up being 1 plus 1 is 2. So now we can figure out what is C2. C2 is just negative C0 divided by, remember, k is 1, so this is 3 times 2, which I know you know is 6, but you can see why I want to write it this way, right? I want to write it maybe as some sort of a factorial here. So I'm going to leave it as 3 times 2, right? Okay, so let's go on to k equals 2. So this will give us C3, which is going to be negative C1 divided by 4 times 3. But remember, C1 was 0, so this is just 0. Moving on to k equals 3, that gives us C4 equals negative C2 divided by, I keep forgetting, so this will be 5 times 4 now? Yep, so k plus 2 is 3 plus 2 is 5, yep. Right, so what is this in terms of C0 now, right? So remember, this is, let's do negative 1 over 5 times 4, and then C2 is negative C0 divided by 3 times 2. So that's going to be a positive C0 over 5 times 4 times 3 times 2 times 1, right, which is 5 factorial. And, you know, just to be consistent here, let's write this as negative C0 over 3 factorial. And I think you can see the pattern, but if you don't, let's do one more. Actually, let's do 2 more, right? Because C5 is 0. How do I know that? Because this is just in terms of C3. This will be negative C3 divided by 6 times 5, but it's 0, right? All right. And then one final one. K is 5, so that gives us C6, which is negative C4 divided by 7 times 6. So that's going to be, right, this is going to be 1 over 7 times 6 times negative C4. So that's going to be negative C0 divided by 5 factorial. So this will be negative C0 divided by 7 times 6 times 5 times 4 times 3 times 2 times 1, aka 7 factorial. Right? So, I think we see a pattern here, and now we could write this as a power series. As it turns out, this is a power series. Remember, that wasn't guaranteed when we first started this. I just said, well, let's guess a power series, because that's what we did last time for ordinary points. Even though this is not, x equals 0 is not an ordinary point, it's a regular singular point, we lucked out. In some sense, we lucked out because we got a power series. So let's write down the power series solution here. So this is going to be y of x is equal to, well, C0, which is our constant, right, plus C1 times x, but C1 is 0, so this is 0 times x, if you like, plus C2. C2 is negative C0 So can I factor out the C0 here? I probably should have done that. I mean, you don't have to, but it might help. So C0 times 1, right? And then plus 0 times x, right? And then minus 1 over 3 factorial times x cubed, right? Times C0, which is on the outside. And then, wait, x cubed? No. This is n equals 2, right? Or k equals 2. No, n equals 2. So this is x squared. Yes. Right. So this is, yeah, C2 x squared, C3 x cubed. There we go, right? So you'll get plus 0 x cubed. And then for the x to the fourth term, you're just going to get C0, right, times 1 over 5 factorial times x to the fifth. And then 0 x to the sixth. And then negative 1 over 7 factorial x to the seventh. Plus dot, right? This keeps going. And we have a pretty good pattern here, right? And in fact, because I left this in terms of the factorials, let's write it as an actual series. I'll have the C0 in front. So here, let's go back to n. N starts at 0 to infinity. And this will be negative 1 to the n, because notice that this is an alternating series here. You have plus, minus, plus, minus. Again, ignore the zeros. So in the denominator, we have 2n plus 1 factorial, right? Because these are odd numbers. So 2n plus 1 represents the odd numbers, right? So, right, again, starting, this is for n equals 0. This will be for n equals 1. This will be for n equals 2. This will be for n equals 3, right? Because we're just ignoring the zeros here, right? So this is going to be x to what power? Well, x to 2n. 2n, because the exponents are even. Oh, they should be even. Oh, I messed up again. Yep, this is not x to the fifth, right? This is x to the fourth, and this is x to the sixth. It's the odd ones that are zeros. Okay, easy fix here, right? So this is x to the 4, this is x to the 6. All right, so I think this is correct here now, right? Yes, good, okay. And, well, so let's match the exponent here. If we want to make these odd exponents, right? And why would we want to do that? Because this is starting to look like a familiar series to us. The familiar series, though, has x to the 2n plus 1. So, but all we have is x to the 2n. So how do I add 1? Well, I would have to multiply by x. And can I multiply by x? Well, sure. Multiply by x as long as I also divide by x. Right? So, yeah, see what I did there? Little trick. I can multiply by x on the inside of the series and divide by x on the outside of the series. And so by doing that, I get C0 divided by x times, right? Oh, let's write this as a series first. If you want to write out the terms, I'll do that next. So n is equal to 0 to infinity. This is still going to be negative 1 to the n over 2n plus 1 factorial, and then x to the 2n now plus 1. Right? And let's write out some of the terms, just so that we know. This is 1 minus, now we get x cubed, right? Same power here, divided by 3 factorial, plus x to the fifth divided by 4 factorial, minus x to the 7 divided by 7 factorial, plus dot, dot, dot. So, yep, by removing the x, or dividing by x on the outside, now I have the same exponents as the factorials, and I don't know what I'm doing wrong here. This is not 4 factorial, this is 5 factorial. Again, easy fix there. 5 factorial, there we go. Okay, now take a look at this and look back in your, I think in 6.1, this was one of the familiar series. This is just c0 over x times sine of x. Right? So this is the Maclaurin series for the sine function. So, yep. So, in fact, we can write this as our c. Again, a c0 is just a constant, right? Times sine x over x. And there's our solution, right? We lucked out, right? In general, we've seen, and we saw this last time, where we get a power series that you don't recognize. That it's just it could be x to the 5 divided by 22,196 or some weird number, and it's hard to tell what they are. In this, we lucked out because the pattern was pretty clear, and we ended up with a very familiar function. Okay. Two problems with this. One, you might think, wait a minute, you're dividing by x here. What if x is 0? If x is 0, you're going to divide by 0. This can't be analytic, right, at x equals 0. Well, remember what analytic means. Analytic means you have a power series, right? And this is a power series. This is a power series centered at x equals 0, right? And if you think, well, but again, you have x in the denominator. How can that be, right? If you look back at our original series here, the one that I kind of crossed out here, before I divided by x, this was just c0 times 1, right, plus 0x, and then minus x squared over 6, and then plus x to the 4th over 120, and so on. So, another mistake. This can't be 1 anymore, right? This is x. This is x to the 1. Oops, bad. Okay, there we go, x to the 1. So x to the 1 divided by x is 1. That's this one over here now, right? Okay, now it works out. Oop, yep, x to the 1, just to complete the pattern here. Although that looks like x prime right now, so x to the 1. Right. So what I'm trying to say is, even though you're dividing by 0, you also have 0 in the numerator, right? Remember, way back in your calculus days, you took the limit as x goes to 0 of sine x over x, and that limit exists, it's 1. So even though it doesn't look like you can plug in x equals 0 here, go back to this power series, you can plug in x equals 0 because you're canceling the zeros here, right? If you expand this out, and maybe I should do that, if you expand this out here, what you really get is c0 times 1, right, minus x squared over 3 factorial plus x to the 4th over 5 factorial. I did it again, right? And so on. So at no time do you have x in the denominator over here, right? That was the original series that I had. So point is that it's analytic, right? That there's nothing wrong with this. So even though the function is sine x over x, and yes, technically it has a removable singularity at x equals 0, we're not going to worry about that, right? The power series exists. When you plug in 0 into this, again, before I divided by the x here, then there was no issue at all. Okay. So that's one problem. There's another issue, though. Remember, originally this was the equation here. Oh boy, way up here. Let me write it down again so that we know that this should be a solution to, right? So this solves the equation x y double prime plus 2y prime plus xy equals 0. And you can double check that it does. Take the two derivatives, plug this in here, and you'll see that it works. It's a good thing to check. But remember, being second order, what do our solutions look like? Our general solutions look like this. So c1 y1 plus c2 y2, right? In other words, we should have two linearly independent solutions. This is just one. Where's the other, right? If this is y1, what's y2? Okay, so that's still in question here. Second order equations have two linearly independent solutions. This is just one. Where's the other one? How do we find the other one? Well, obviously this didn't work, right? We assumed that this was a power series up here, and we did all this work, and you know, when you have an ordinary point, usually what happens is you get a recurrence relation and you get two linearly independent solutions. But this time we just got one. So that's bad, right? That's pretty bad. However, if you remember way back in section 4.2, right, when you have one solution and you know there's two, you can find the other one, right? Just use reduction of order, right? Remember what you do there? We're going to assume that our y2 looks like this. It's going to be u of x, some function of x, times y1 of x, right? Eerily reminiscent of variation of parameters, right? It's kind of the same idea here, right? So, yep, you can form this, plug that in here, and then figure out what your u has to be. Again, rather than do all that, it's a lot of work. We're going to take the shortcut, right? So this is a formula you might have to look up in your book, which is fine. You're welcome to do that. When you do all that in general, this is the formula you get. You get y1 of x times the integral of, and then this fraction here, e to the power negative integral of capital P of x dx divided by y1 of x squared dx. Okay, so this is the formula for reduction of order, right? This is the reduction of order formula. And so I'm just going to use this, plug in y1. This is my y1 here now, right? This is y1. And plug that in here, and let's see what we get for our y2. Okay, so what do we need here, right? So what is this p of x? Because that's what we're going to have to integrate in the exponent. Well, the p of x is, if you remember, that was the way up here. Yep, that was 2 over x, right? There, way up here is the p of x. So 2 over x. Yep, so let's write that down here. P of x is 2 over x, right? Notice that this doesn't even depend on q. Okay. All right, so, yep, so y2, I don't know if I have enough room here, but I'll try it again. y1, and we know y1 is just sine x over x, right? Times the integral, big integral here, because in the numerator we're going to have e to the negative integral of 2 over x dx. And in the denominator we're going to get y1 squared, so sine squared of x over x squared dx, right? So let's see here. This x squared will come on top, right? So this will be x squared over sine squared of x times e to that integral. Now, right, so what is this integral going to be? Well, it's just going to be negative 2 log x, right, plus c. We don't bother with that here, right? I don't need dx anymore. I need the dx for the whole thing. And remember, this is just going to be log of x to the negative 2, and the e will cancel the log, so this is just x to the negative 2. We still have to integrate, right? We get x squared, and then all of this, right, this is just x to the negative 2. So how fortuitous, we get x to the 0, right, divided by sine squared of x dx. So this is just 1, right? And so now we just have to integrate, well, first of all, sine x over x is on the outside. Then we integrate 1 over sine squared, which you hopefully remember as cosecant squared. And that's a pretty easy integral to do, right? the integral of cosecant squared. Well, the derivative of cotangent is negative cosecant squared, so the integral of cosecant squared is negative cotangent x. Right. Plus c, but we don't need the c here, right? All right, so that's my y2. Yep, we'll just clean it up a bit, right? So this is sine x, right, over x, and then cotangent is cosine over sine. And you can see that sine divided by sine is 1. And so we just get negative cosine of x divided by x. You don't need the negative here because that's, whether it's -1 or +1, it doesn't matter. It's our c, right? We're going to multiply by c2 here for our general solution. Okay, so so if just to conclude here, our y1, right, was sine x over x, and we probably should have guessed that y2 would just be cosine x over x. That's like, yeah, that's a big duh here, right? We probably should have known that. But, reduction of order will tell you that, right? So, yes, what happened here? Why didn't this method give us the second solution, right? And maybe I should just write down our final answer. So our general solution, y of x, will be c1 sine x over x plus c2 cosine x over x. And that solves the original equation, which I keep erasing, but just to remind you, xy double prime plus 2y prime plus xy equals 0. I think I'm missing a minus. Where was the minus sign? Oh, no, I think that's it, right? Yeah, they were both pluses. Okay, never mind. All right. So I left you with the question: what went wrong? Why did we have to use reduction of order to find this solution here? And well, remember when I said sine x over x? This is analytic, even though you're dividing by 0 here. When you take the limit, right? It's finite. It's 1. This, however, is not analytic. Right? We cannot expand this as a power series. Well, let's try. Let's see what happens. We get 1 over x times cosine. Now remember, cosine is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. So when you distribute the 1 over x here, you still get 1 over x minus x over 2, right, plus x cubed over 4 factorial, which is 24, and so on, right? So this is x to the 5 over 6 factorial. I forgot what that is. 120 times 6, 720. Yeah. Anyways, it's this 1 over x, right? We didn't have that for the sine series, right? Well, we had 1 over x here, but that multiplied x. So the lowest power of x for the sine series was x to the 0, way up here, right? But now it's not. Now it's x to the -1, right? Minus 1/2 x to the 1 plus 1 over 24 x to the 3, ... So that's what went wrong. The cosine term here, the second linearly independent term, is not analytic because the series involves a negative exponent. And remember, a power series, well, let me go way back up here. What is a power series? Starting at 0. No negative exponents in it for a power series. So that's what went wrong. This is not a power series anymore, right? So yeah, this is not a power series. So that's our issue here, right? So I think in the next video, I'm gonna leave it at this because this was a long problem. It took a while to get, and so in the next video, I'll show you how to fix that, and so we can get a series that might not be a power series, but it's still an infinite series. In other words, I don't know about you, but I'm perfectly content with representing the solution here, the y of x, as this. This is the answer. The only difference is, though, that it's undefined at 0. So the interval of convergence, right, the interval of existence here, in other words, the domain of the solution, will have to be 0 to infinity, but not including 0 anymore, right? Even though you can do it for the first term, you can't do it for the second term, right? So that's the only thing. We're just going to have to, eliminate 0 from the solution set. Eliminate x equals 0, and just take any other number. For every other number, this should work, right? Okay, so I hope that helps at least explain why we cannot use a power series when you have a regular singular point.